So I got 8 pi. 8 pi is my volume. I don't have units on any of these problems, by the way, but they are, whatever meters cubed or whatever. There's going to be some linear unit cubed. This one kind of looks like a classic beehive, doesn't it? Yeah, it kind of does. Anyway, here's a summary of what we've got so far. We're doing something called volumes of revolution. All the ones we're doing now, we're calling them simple. It means they don't have a hole going through them. They're a solid object. We'll get to the other ones next. All right, we can revolve them about the x-axis, and we have this simple formula for volume. We can revolve them about the y-axis. We have this simple formula for volume. So now let's take a moment, look at your book, chapter 7, 7.3 is the section on volume. It's page 407. We're going to start by looking at number 14. So they give us the equation y equals x minus x squared and y equals 0. These are the equations that bound the region, and then we're rotating about x-axis. That's an important thing we need to know from this problem. All right, so I didn't copy over all the information from the problem. It's here. It's number 14. So here's our two equations. The directions say, find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. All right, so the region is bounded by this line and this curve. All right, and it's revolved about the x-axis. All these are x-axis revolutions. Okay, so what are we going to do? First, we should draw it. All right, so we're going to draw it. Now, you should be just really expert at drawing this. Look, this is a parabola. It faces down. The x-intercepts are 0 and 1. You hardly need to spend time factoring that. Faces down because the leading coefficient is negative. All right, so that's what you got. You got 0, you got 1. We're rotating it about the x-axis, so we're basically going to mirror this down here and rotate it like that. And what do we got here? We got a football. Yeah, it's just a football. Probably some fancy mathematical name for it, but I don't know what it is. It's like a oblate spheroid or something. It's not, though, because it's a parabola. It's not. I think the spheroid is actually based on an ellipse. This one's based on a parabola, so it's really sort of a type of paraboloid. I don't know if it's technically a paraboloid or not. Anyway, it's a football. Look it up if you're curious about the name. I'm not convinced it has one. All right, so how then, you say, how are we going to actually do this volume? It's going to be so simple because we're just going to use this x-axis revolution formula. All right, you guys are all a party to the x-axis revolution. The axis of x. So we're going to go v equals, I'll go ahead and write the formula for us, pi integral a to b of f of x squared dx. I like to write the brackets. Not everybody does. You do have to think about where these limits came from of 0 and 1. They came from the x-intercepts because the other line was y equals 0. Right? You're really solving 0 equals x minus x squared. You're going to get 0 and 1. So that means that our volume is pi integral 0 to 1 of our f of x, which is x minus x squared. Squared, don't forget that. Don't forget the squared. Don't forget the pi. I'm going to forget them all the time. Integral 0 to 1, don't drop the pi. Square this out. It's not too hard to do. X squared minus 2x cubed plus x fourth dx. All right, and then, you can finish the integral. Should I finish it for you? All right, fine, I'll finish it for you, just show how easy it is. So I have pi times x cubed over 3 minus x fourth over 4 plus x fifth over 5, and we're going from 0 to 1. The 0 gives us all zeros. I usually like to write the 0, but I want to be expedient today, so I'm going to show you, at least on this problem, although I'm having a little trouble managing objects on my desk. All right, there we go. So I'm just going to plug in the 1s. If we plug in 1, it's nice and easy. So we usually have pi times 1/3 minus 1/4 plus 1/5. Oh, is it 1/2? It's x fourth. Oh, see what I get for rushing. This should be 2x fourth over 4. So that means this is x fourth over 2 right there. X fourth over 2. Should never rush your problems. I just got here and I just remembered what the solution was. It's different from what I was looking at there. All right, and then I'm going to go, 1/3 minus 1/2 is negative 1/6. 1/5 minus 1/6 is 1/30. So it's pi over 30. Don't need a calculator for that. All right, let's see. Let's go ahead and look at number 24. All right, so number 24. So number 24 on that same page, it gives you, so one of the things that's different is it asks you to revolve about the y-axis. So number 24, says in exercises, we're going to do it here, 23 to 28, find the volume of the solid generated by revolving the region about the y-axis. So I chose 24. X equals y to the 3/2 power. X equals 0. Y equals 2. All right. So x equals y to the 3/2 power. So what does that look like, you say? Well, this is one of the areas where the Casio is a really nice calculator because you can just very easily switch everything to x using the type button. So you type x, and then x equals 3⁵ power. I drew it on a standard window, and it looks like that. That's all I need to know about it. It sort of looks like a square rooty. Looks a little square rooty. All right, so I got a thing that goes like that, and then I got the line y equals 2. Am I going to need to find this x at this intersection point? I am not. All right, now I got to rotate this around the y-axis, right? Around the y-axis. So let's create a mirror image over here. And how would you describe this shape? How would you describe it? I usually call it a funnel, or some people say it's like a tornado. It's also like if you think of one of those coin things, you know, where you throw a coin down, and it's like, but it's just like it's like very flat, maybe like a trumpet horn, right? It's very flat on the top, and then but it flares out. But the whole thing is solid. All right, so it's like if you took a very flary trumpet, filled it with cement, and then pulled out the cement. All right, it looks like that. Spinny top maybe, but too flat on the top to spin, it would fall over. All right, now how do I do the volume? See, they very nicely already solved it for x for me, because this is revolved around the y-axis. Since we're revolving around the y-axis, revolve about y, that means I want to do my integral dy. That means I need to solve for x. So if they hadn't already solved x for me, I would have to do that. But we already have solved for x. So we can just go that the volume is equal to pi times the integral from a to b of f of y squared dy. So that equals pi times the integral. Okay, so important thing to bear in mind is when we're integrating with respect to y, the limits are y coordinates. The limits are y coordinates. All right, so that means I'm going from y equals 0 to y equals 2. 0 to 2. All right, and then my function is y to the 3/2, and I got to square that, and it's dy. So then I have pi. I should always simplify my integrand as much as possible before I proceed. So I just multiply these exponents. I get y cubed dy. So I get pi times y⁴ over 4 from 0 to 2. So 2 to the 4th power is 16 divided by 4 is 4. So we got 4 pi. Bam. Easy, make it easy. So important things to remember when you're looking at these, right? So these are our two main formulas. When you're integrating with respect to y, this f of y needs to be solved for x. So it's going to be, you know, x equals f of y. And these limits of integration are going to be y coordinates. Whereas when we're integrating with respect to x, the limits of integration are x coordinates. So that's an important thing to keep straight on these two. Okay, next we will look at another example and the ways that this can get even weirder, because it has not gotten weird enough yet.